Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So thank you all for coming. It's nice to see a bit of a crowd here. It's my great pleasure to introduce Jonathan Edwards from MIT. And I happened across an article he wrote for Uppsala some years ago. And it really stood out and caught my attention. And I sent him only my second fan letter ever. And, well, here he is to talk to us. And I think this topic is kind of different, but really important. And we should remember that Visual Studio, the visual, it's not an accident. It's perhaps more aspirational than real, but it actually, there's a lot of promise there. And I think this stuff is exciting.
Well, thank you, Herman. Thank you for inviting me. I'm happy to be here. Hotbed of research these days. And I suppose I should throw out a caveat that this might not be the standard research presentation that you get here. Well, it certainly isn't that we get at MIT, because I don't have substantiated results to report, and I'm not actually claiming any real results here. I'm just throwing some kind of semi-crazy ideas out on the table and hoping to spark a conversation about it. So I'm talking about conditionals today, if statements. And what I want to do is present a visual formalism for representing conditional logic that's based on tables. And the basic idea is that tables have two dimensions, and I use one dimension for representing logic and the other for representing computation. And because they're orthogonal, there's some nice properties. So to motivate things, I want to start off with an example, which is here's some trivial Java, or I guess equivalently C# code. And the question is, when is x set to 3 by this code fragment? And we know that if a is true, that we're going to fall in that branch and set x equal to 1. So a must be false. And if b or c is true, we know we're going to set x equal to 2. So that has to be false. And by De Morgan's laws, that means b is false and c is false. So a, b, and c all have to be false for x equal to 3. Easy, sort of. But let's say that we hit a bug in this code, and what we want to do is whenever b is true and c is false, we want to set x equal to 3. But we want to keep the behavior of this code unchanged in all other conditions. This is the bug is specific to this case. And we don't want to duplicate any code, because even though these are trivial little one-liners, maybe they're big hunks of snippets of code, and we don't want to duplicate all over the place. So we know we have to exclude b and not c from the first then branch. So that gives us this formula to insert in the first conditional test. And applying De Morgan's laws, we get that. Likewise, we need to exclude b and not c from the second if test. That gives us this, which any competent programmer can see is equal to that, obviously. But that's not the answer, because the first change we made in the first conditional test had a side effect on what conditions flow through to the second conditional. So I made this mistake in the submitted version of the paper that this talk is based on. And so you tear it apart and start all over again and try to figure it out. So far, I haven't met anybody that could solve this problem in their heads without pulling out a piece of paper and doing algebra on it. And this is 6 lines of code and 3 variables, right? So what's wrong with this picture? We're doing Boolean algebra in our heads when there's a computer sitting right in front of us. Meanwhile, the computer is emulating a teletype, right? This is absurd. So I want to show you some steps and some ideas for how to solve this problem. Subtext is a non-textual programming, an experiment in non-textual programming. Whoops. Let's go to the code. So the world of subtext is a tree. And I'll walk down this tree to this code, which is that Java code we set off. Now, this is actually called a decision table. These were, it's a variant of a truth table. Decision tables were popular for a while in the 60s. They The ACM, in fact, distributed a decision table programming language, but they died off. The first column here has the variables of the table, A, B, C, and X, and these arrows indicate which are inputs and which are outputs to the table. The second column applies assertions onto the variables. You can think of that for the moment as type declarations. The first column here has this yellow box. Is it yellow for you? Yeah. Which is a condition that tests the value of the variable of its row, and here it's testing whether it's true. And this value down here, 1, is a conditional assignment to the variable of its row, which is x. And the rule is that if all the conditions in a column are satisfied, the column is true, and all the values in that column get assigned to their variables. If we look over here at this column, that answers the first question about the code. Right? X is equal to 3 when A, B, and C are false. And we didn't have to think about De Morgan's law to figure that out. We just obvious by inspection. This column's a little more complicated. It's divided into 2 subcolumns. This is a disjunction, right? So the rule is that if all of the conditions in a subcolumn, any of the subcolumns are true, then the entire column is true. So this is just disjunctive normal form, right? Which is a normal form and can represent all Boolean propositions. Now, the law of decision tables is that exactly one column must be true in all cases. Or rather, in all cases, exactly one column must be true. So there can be no overlaps when 2 columns are true at the same time, and there can be no gaps when there are no true columns. And that's what makes the logic of the table very easy to understand. When there's no overlaps and no gaps, we call it a partitioning. So there's no else's. Everything is explicit. All right, so let's fix that bug. So we do that by adding a new column, which is creating a new case. And what was it? It was B and not C. So we'll create a, now you see the column popped over here. I'll explain why later. And I'll say C is false. And now what we want to do is, in this case, we want to set x equal to 3. So I will drag and drop that condition over onto the 3. Now, the table's complaining about overlaps. These values here are possibly true in the same cases. And I can use these things to go in and explore the cases, but we know exactly what we want to do here. So I'm just going to approve this column. And there we go. So it did the Boolean logic for us by maintaining the partitioning invariant of the table, right? That's what forced it to do the correct Boolean algebra. So we can just read that table out into the correct Java code. Okay, great. There's only one problem. Decision tables just make decisions. They can't actually do anything, right? You still need to write code to calculate the values of the variables that are being tested and to do something with the value of the variables being assigned. So, and then you get this mixed world of code plus decision tables and tying them together, and it's kind of messy, and so no one's been really seems interested in doing that. So what I'm going to talk about today is adding a language of functional expressions into decision tables, producing what I call schematic tables. And we'll start with the inevitable computer science example of Fibonacci. So let's take a look at the schematic table for Fibonacci. So here are the variables. There's in, which is the input argument, and out, which is the result. The assert column is asserting that the input is non-negative. So assertions are actually runtime assertions. They aren't type declarations. But we'll see that sometimes they behave like type declarations. This column here says that if the input is 0, the output is 0. If the input's 1, the output's 1. And here, in the greater than or equal to 2 case, is the interesting recursive logic. Now, that is expressed here with this stack of boxes and lines. Each box is a function call, and it's on its own row of the table. This box here is a call to the subtraction function. Its left-hand argument is the input of the overall function. And its, right-hand argument is the constant 1. And the result of that function flows down this line into the left-hand argument of a recursive Fibonacci call, which then flows down into this addition function. So this is really analogous to parenthesized expressions. And when you're composing a function through the first argument, what you end up with is a vertical stack of boxes like this. When you compose through subsequent arguments, you get another vertical stack, which is indented. Now, it's actually a graph underneath here, not a tree. And the function arguments are connected to each other, and I do a spanning tree. I pick a spanning tree out of that graph. The edges in the spanning tree are these vertical lines. The edges which cross the spanning tree are these symbolic references. Like here, you can see there's 2 references to the in variable. Now, you could argue that this is slightly easier to read than parenthesized expressions, mostly because you can read it up and down, whereas it's hard to read parenthesized expressions inside out, at least for me. But it's also easier to edit. And I want to show you that by writing Fibonacci. So let's create a new function. Let's call it fib. And here we have starting point of a standard unary function. It's got the input and the output variables. Now this table says it has a gap. And this question mark means it's missing an assignment for the output variable. And it's missing it in all cases because we don't have any code here at all. Okay. So all right, so let's add some code. Let's add those base cases. So now here, this is a condition editor. So you see I get to choose from a small list of predicates. And I get to put a value. So in the case that it's equal to 0, I want to return 0. Now you can see it calculated the gap as being non-zero. Let's add the other base case. Now you see that pop to the right of the 0. The columns are automatically ordered. Everything's automatic. All the layout's automatic here. The ordering of columns is chosen so that it's what you'd expect, that equal to 0 comes to the left of equal to 1. Okay, so now the gap is not 0 and not 1. Well, we know we don't want to deal with negative numbers here, so let's put in an assertion that the input is greater than or equal to 0. So now the gap has been calculated as greater than or equal to 2. So the schematic table here understands the logic of integer ordering. Right? This is not just Boolean logic anymore. Now we need to actually write some code. And the way to do that, the easiest way to do that is by splicing in functions. So what happens here is I added a function call to unknown function represented as f question mark with an unknown argument. Well, actually, that argument was what was here before. See, what happens is I replaced the question mark with a box, and the question mark became the argument to the box.
Can I ask a question about
Yep.
A couple steps back? How does it know that the n is an integer?
That's good. It knows it's an integer because currently I don't have any other numeric types implemented. And so the fact that I'm asserting that it's greater than or equal to 0 implies that it's an integer. And if I had put in rationals, I would have had to add the assertion that it's an integer there. So that's good catch. So we want to make this a recursive call. So I'll edit this. Now you see as I'm typing in Fibonacci here, it's completing it. This completion is based on a full text search of the code, the comments, the libraries. There aren't any libraries yet, but basically it's meant to Google your code. Type in a bunch of keywords, whatever, and it's going to come up with a ranked list of hits, maybe with little cute little snapshots showing their contextual stuff. Could do a lot of cute things there. The point here is that it's not a name. It's a set of keywords to be searching on. And when you hit enter, or when you pick something off the list here, what's going to be recorded in the program is actually a persistent link in the underlying data model of the program. The actual keywords you typed in are forgotten. So name binding is not part of the semantics here. Everything is persistent links, and we use names only at edit time to help you find what you're looking for. And in fact, if you can see what you're looking for, you can just click on it like that. Okay, now the question mark turned red. And the reason it turned red is because question mark is not greater than or equal to 0, right? It knows that Fibonacci, if I open up the Fibonacci, it's got a greater than or equal to 0 assertion on it. So that's kind of like a type check, isn't it? But there's no types here. Anyway, let's splice in a subtraction function. And yeah, both those arguments don't type check yet. And okay, now we know we need an addition down here. Now here you can see why splicing is called splicing, right? Because I essentially took that line there and cut it in half and inserted in a new box stacked up with the other two. It seems like splicing is really how I can do most editing. Anyway. Okay, now what we want to do is the second Fibonacci call. And so what we should do is drag and drop a copy of this stack over here. But I haven't implemented that yet, so I'll just do it by hand. What? Sorry, what did I just do? Oh. That's the input argument. And no, that's supposed to be, sorry. Right? Now you can see as I was editing here, it lays everything out automatically. All I'm doing is I'm making and breaking links between functions in this graph. And the layout is computed automatically. So I think of this as graph level. You're editing the data flow graph, basically, instead of, yeah?
Can you also put an assertion on the out area?
Yeah.
And then you verify it.
I'll come back to that. I'll come back to that because, yeah, that might be interesting to this crowd. So I think of this as directly editing the data flow graph. I get a lot of pushback on this concept, but it seems to me that when we're normally in a text editor, we're doing insert delete operations in the text, and we're thinking in our mind how to choreograph that to produce a desired change in a data flow graph by inserting and deleting little pieces of code and inserting them in the right place so that the parentheses still balance. And we're adding carriage returns and white space to help us read that nested structure of parentheses, which is perfectly edited. And this just seems to me easier to do, and you're more directly expressing what you're doing. But some people disagree with that, and I suppose I need to do user studies.
By easier, what do you mean?
Less thinking.
Certainly not less clicking.
Certainly not less clicking, although I believe this could be made as fluent as Emacs. There's no reason why you need to use the mouse here. You can curse. It's hard. It's 2 dimensions, so cursoring around makes perfect sense. And everything's the keyboard. And since you're not, in automatic edit mode where everything you type is automatically changing, keys can mean functions and stuff, like in VI. So, but that has to be worked on. I guess what I'd say instead of thinking is that you can get your results with fewer errors, right? So if you're hacking around on the code there, it's very easy to make an expression which doesn't parse and doesn't make any sense whatsoever. Here you're making higher level logical changes. And ideally, you've got tools making some of those changes for you. All right. Anyway, so let's test it out. Okay, this is all red and angry because I haven't given it an argument to the Fibonacci call, so let me just do that. Okay, what's new here is this blue column with an equal mark. These are values, and 2 is the value of Fibonacci of 3. This assertion here was automatically generated with the test, and it's saying the result is not the exclamation mark, which stands for the universal error value, or ideally the super type of all error values. So you normally don't want your test to throw an error. But if we look inside the call, we see the blue column again here, which is showing us the value of every internal computation that takes place. And this is why having each function call on its own row is handy, because you can see its value. These two columns here are grayed out because the conditions are false, or unsatisfied rather, so they're darkened and their columns are grayed out, and the live code is still out here in bright. And if we drill down into another call, you'll see that the pattern is different. Here, this column executed, and the code in these columns is grayed out. And we can arbitrarily look around. Another nice thing about this function per row is that it really works nicely with this tree expansion metaphor of browsing. So you can drill down into the call tree. So this is, I think, a lot nicer way to debug than setting breakpoints and running to that point and having a little peephole at your current state. It essentially gives you this God's eye view of the execution of the code. And so I call this example-centric programming, and there's lots of the better paper I wrote, which is what impressed Herman, was about that and the implications on programming methodology, where you could start with your examples first maybe and then write your code around it, sort of like test-driven development. Anyway.
Can you add additional test cases?
Yeah, sure, absolutely. And in fact, this isn't really a test case yet, but I can turn it into one by double-clicking on the 2 here. And then it just changes that assertion to say the current value is in fact good and should remain that. And if you break the code at some point in the future, like, well, the result's no longer what it's expecting and it's red, it's a failed test. And so essentially, unit testing is built in here instead of having to add another code framework around to do it. It's kind of in the semantics of the language. And the key fact here is that as I was editing the code, right, it's still executing. So this is a live programming language, like a spreadsheet, right, that there's no difference between edit time and compile time and run time. There is just programming time. And I think that's a nice conceptual simplicity.
What if you introduce a loop, an infinite loop or infinite recursion?
Right, so it's lazy. And it also has bounds on how far it's going to do it. So at some arbitrary, like Stack Overflow limit, it's going to say, you've gone too deep here, and just start returning errors. But it will do the infinite recursions lazily, only on need. Okay, so it's like a spreadsheet, but unlike a spreadsheet, it's Turing complete. It has functional abstraction. It has recursion. It's a real programming language.
I'm thinking that I'm going to miss breakpoints.
You're going to miss them? Really? Why is that? Seriously?
Yeah, seriously. So,
well, you should ask me, though, what about side effects, and global state and all that, because this only is working for a pure functional program. And then you should go see this other paper I wrote, but which I didn't publish. It's just a tech report. So I do have a story on state, but it's a long story, and I'm happy to talk about it offline. And it's not a complete story. It's really kind of a little sketch of a story. But so if you're willing to talk about functional programming, this is cool. But functional programmers have some cool debuggers too, although not as clear as this, I don't think. Any of them I've seen. Okay. All right. Moving right along. So here they are, side by side at the same font size. And I actually measured this, and it's almost exactly the same amount of screen space. But Fibonacci's a trivial program, right, and unconvincing. What we need is a more realistic program. So here's a program that contains an if statement, an if expression, and 2 switch statements. The idea, my son actually laid this out for me, is this is some code from a video game that's calculating the damage of an attack. And so the attack is an enumeration. It might be either a magic or a melee attack. And it could be a surprise attack, which changes its damage. And the defender has some defense level, which I just thrown in as an integer here. So to see what this code is doing, it helped to slice out the code. So here is the code that executes for magic attacks. And we can see that it sets this power variable to 5, calculates the effectiveness of the attack as the product of that power and something having to do with whether it's a surprise attack. Then it calculates if that effectiveness overwhelms the defense, then the damage is the difference. But if it doesn't, then there's 0 damage. Here's the slice on the melee attack. It uses a different power constant, uses the same effectiveness calculation, and it uses a different effectiveness algorithm, supposedly because magic and melee have different laws of physics, governing them. So, okay. How do we do this? Let's open. Now here's the schematic table. Now this is got some new things going on in it. First of all, there are multiple decisions being made in this table. So far, everything I've shown you had only one decision per table. So this row here, power, is deciding between 5 in the case of magic attack or 4 in the case of a melee attack. And this unnamed row here is deciding between 3 for a surprise and 2 for non-surprise. So the partitioning rule has generalized so that it applies to each separate decision. So every decision is made in one row, and all the choices made in that row must be a partitioning. So there's always one chosen, and there's always exactly one true. But those are independent between multiple decisions. The result of that decision, the first one here, flows across this horizontal line down into the first argument of this multiplication. And the result of the second decision is flowing into this. And then the result of that multiplication forks out across these two different places, which correspond to the code in that second switch statement. So what's happened here is that I had that tree of boxes before, and what I've done is I've splayed it out horizontally across conditions so that the functions are in the conditions where they execute. And the horizontal lines show you data flows that cross. The final decision here is captures all the return statements from the Java. So here, if the result of this subtraction is non-positive, we return 0. If it's greater than or equal to 1, that means positive, then the value itself is returned, which is nice that I didn't have to repeat the subtraction or create a local variable like you usually do, because the lines let me do that anonymously. And here's the calculation for the melee case. It's the division and the multiplication. Okay, so let's slice this program. I don't need to use PowerPoint to slice it out. I can do the same thing just by double-clicking on a column. And what happens is that column is shown in green, meaning the conditions in that column are what the table's been focused on, and any columns whose conditions contradict those conditions are hidden. So the magic columns were hidden. If I focus on magic, now the melee column is hidden. And this lets us see the actual complete rule for column ordering, because the way it works is that logical implication between columns always goes leftward in the table. This column here is magic and less than or equal to 0, which implies just magic. So it has to go to the right because it implies that column. This column here is true in all cases. Everything implies true. True column has to go on the left. A false column has to go all the way on the right. These purple columns are columns which are neither implied by or imply the focus column. And they're not contradicted by it either. So these are cross-cutting conditions. And if you're familiar with the idea of a Boolean lattice, focusing the table is a slice of the lattice. You're at one point in the lattice. The things upward in the lattice are to your left. The things downward in the lattice are to your right. And the things that are incomparable are over in purple. So what I like about this is that it's really kind of materializing Boolean algebra. You can actually see what the logic is to a certain extent once you understand the rules. All right. Okay, so now what's up with this column? The multiplication is sitting in a true column. This is based on relevancy analysis. What I do is I follow the data flow from the outputs of the function, adding up all the conditions that are being chosen. And so I can infer when each function's result can possibly flow through to the output of the whole function. That's when it's relevant. Because this is a lazy functional language, that's also the only time it'll execute. But I'm showing you that by placing it in a column showing its relevancy conditions. The relevancy conditions for this are true because it always executes. Both of these paths use its result. If I was to change the code, so for instance, let me break this link. You'll see now multiplications in the magic column because that's the only time it's used. If I break that link, pops over here into a false column. It's dead code now. So what's nice is, in imperative programming, we have to pick and choose exactly where our function calls are executed to make sure that that is executed in all the right cases. And in a lazy language, you don't have to do that, but you lose the knowledge of when it's executing. And I think it's actually important that you know when this is when it's going to be called so you can tell whether it's correct or not. Anyway, it's just another example of revealing the logic. Okay, so now the point I want to make here about tables in general is that if you look at this column here for melee, all of the code specific to the melee case is in this column, whereas in the Java it's split across two different switch statements. So this is called cohesion, right? And it's generally thought to be a good thing. So what's going on here? Here they are again at the same font size, and now I use fewer pixels even. Because obviously there's a lot of plumbing in the Java, and there's a lot of wasted white space over on the right-hand side in most code. If we look at the control flow of the Java code, where blue is magic and red is melee, we can see that this green box here is the common code that executes in both cases, and it's smack in the middle of the control flow. And so the decisions we make beforehand have to go above, and the computations we make from the results have to go below, so we have to duplicate the switch statement. And we could, instead of duplicating the switch statement, we could have duplicated something else or used some higher order functions. But the point is that this is sort of a design dilemma we face all the time. The nice thing about the table is that the related logic is in adjacent columns. All the stuff representing the magic case here is in blue, again, red for melee and green for the common code. And it's these horizontal arrows crossing between columns that show you data flow that jumps around between different cases. And the reason that you get this less duplication and better cohesion is just that there's two dimensions in a table, whereas the text only has one. So, and with the one dimension, that essentially causes a traffic jam. So, here's the central idea. It's not a big idea, really. It's just that by using the two dimensions of a table, we can represent deciding and doing orthogonally, independently. Deciding is all about logic. The semantics is just Boolean algebra, right? It was worked out 200 years ago or so. The presentation is with partitioning of columns. The vertical dimension always goes downward. It's all about computation. The semantics are that of a functional data flow graph, and the presentation is based on a spanning tree. So we get this nice result that these two very different control structures collapse into the same thing, essentially, in a single representation of a table. And to me, that's a good sign. But it's not, the story is far from complete, because there's another major form of conditionality that we use all the time, polymorphism. And in fact, many people would recommend that we refactor that program with the switch statements into classes and use polymorphic dispatch as a cleaner way of doing it. So here is that refactoring. Here in green is the abstract class attack. And the common effectiveness code was moved up here into an effectiveness method. The magic class is subclassing it and overrides the damage method and a power method. Power is an abstract method up here in the superclass. And then likewise melee. And if we look at the control flow here, so a magic attack, let's say, would do a dynamic dispatch from the abstract damage down to the overriding damage here, which would then do an up call to the effectiveness method in the abstract class, which would then do a dynamic dispatch down to the overriding power method, and then you'd back up the stack. And here's the flow for the melee case. Now, of course, this is not quite fair because in practice we typically only see one class at a time on the screen, so it's really not this simple.
If you just made the effectiveness come into a procedure, what if you forget it?
Procedure. Procedures, what are those? In Java?
Those are old-fashioned ideas that have been abandoned in favor of this.
Oh, hi, what are you doing here? Right, well, that's another story. Back. So, how do we do that? But there is a story to be said here about what's useful about polymorphism. Here's the polymorphic method of a version of damage. Well, it's the same thing. This is a fraud, right? The only difference is that I'm using class membership tests now. Instead of testing for an enumeration value, I'm testing whether the attack variable is a member of these different subclasses. Everything else is the same. Where are the classes? Where are the methods? Okay, well, here's the melee class. There's all the code that was sitting in the melee subclass in this one column, and focusing down eliminates the irrelevant stuff. But in addition, I'm seeing the effectiveness code that I'm inheriting. So here again, the Boolean logic is showing us that what we inherit is leftward in the table. Actually, let me show you let's focus on the magic class. So here's all the logic from the magic class. And what gets inherited is off to the left. And these overriding methods on calculating this, were those overriding methods? I don't remember. Oh, well. Okay. Okay, so, I mean, what is polymorphism, really? It's about spreading your code over a class hierarchy, right? You divide it up into these methods, you place the methods in the class hierarchy, and then you let class testing, you let method dispatch do your if statements for you, right? It figures out which of those methods to choose. Well, so what is a class hierarchy, right? It's a nested partitioning. And tables here are naturally good at representing partitioning. All we have to do is add some logic for nesting. So, gotten out of sequence here a little bit. And actually, I'm not seeing any nesting yet. So what I'm suggesting here is that instead of dividing your methods, your logic up into little methods and spreading them over a class hierarchy, you put your method into a table which has choosing to make decisions based on class membership. And then you can focus in on that table to get that same method-oriented view. With the slight caveat that it's not just the method, it's also you're seeing inherited and overriding code in that same focused view. But there's an argument that that's actually a good thing. So focusing is essentially logically not a method, but a slice of the whole of that method up and down the class hierarchy. You know, and you can get those kind of views, at least in Eclipse, and I'm not sure about Visual Studio. I haven't tried that yet. But unlike methods, it's a lot easier to share code here between methods. So I didn't actually have to break out effectiveness into a separate method. It's just some code sitting off there to the left that's shared by all the different quote-unquote methods. And it's also very easy. I could add in conditions combining testing on class membership with other things like whether or not it's a surprise attack. And that's really hard to do in simple polymorphic languages. You'd have to go all the way to predicate dispatch to be able to do that kind of stuff. So in practice, we end up refactoring back down to if statements when we need that. I should mention that, predicate dispatch is really what this is about here, and that was the main insight about how to encode polymorphism into a table. Because overriding is just a matter of implication. Well, let's talk about overriding then. So overriding is what makes polymorphism work. So to do that, let's add a new kind of attack, a ranged attack, and we want the ranged attack to work just like a melee attack, except we'll have a different power constant. So here's that refactoring. So I've moved the melee code up to this abstract physical class, and then I've subclassed melee and subclassed ranged, and then in ranged I override power. Okay? So both melee and ranged are physical versus magical attacks. Let's do the same thing here. I'm going to open up the class hierarchy in a separate pane here. So here we see that melee and magic are both subclasses of attack. Attack's a subclass of object. And what I'm going to do is I'm going to splice in a new superclass here. Call it physical. That was the same splice that I did before when I was editing Fibonacci. This is, it's a prototypical language where pretty much class hierarchy, class relationships, and instance relationships, and even variable values, it's all the same stuff. Now we want to create a subclass of physical, and we want to call it ranged. Okay, now as soon as I did that, you see it popped up this gap in the table. This is telling us that in the case of ranged attacks, we don't have an output value returned. Now you can also see here the display is showing us how our classes stack, what the tree structure of the class hierarchy is. So physical is on top of ranged, so melee and ranged are subclasses of physical. So it's nice for this gap to pop up. In Java, we might have gotten an error about failing to implement an abstract method. But rather than a compiler error message, this is actually showing us in the code where to fix and actually kind of giving us the boilerplate for the fix. Now, we said what we wanted to do was for ranged attacks to by default be the same as melee. So what I'll simply do is I'll drag those conditions over and merge them here. And now what was split between the melee and ranged is now just in the physical. So that got upgraded to physical. But we need to override this value 4 in the case of a ranged attack. And the way we do that is we focus first on what we want to override. So I'm going to focus on a child of physical, which is ranged. And now we have the table focused on ranged. There's nothing in this column because there's no specific logic for ranged yet. What I want to do is for power to be 3 when it's a ranged attack. So I'll just go and do that, edit that cell. And the 4 disappeared because we're focused on ranged, and that's incompatible. But it's not gone. If I focus back out here, we can see what really happened was that the 4 is now only applying to melee attacks. It got downgraded from the physical down to melee. So what's happening here is that when you edit a focus table, you can make any changes you want to, but those changes only apply in the focus conditions. The logic outside of that focus conditions is guaranteed to remain exactly the same. So to do that, it moved 4 there. So that's what overriding does, right? You've got a specific case, overrides the more general case. It's just this is being done at edit time based on this logical analysis instead of at runtime based on method dispatch. So it's almost the same thing as overriding, because if I unoverride, the 4 should have moved over here, right, popped back up again. And you know, I've debated that. It leaves a gap here now. We've got to decide what to do. And we could, you know, promote the 4 up there like that, which is what would happen if we just deleted an overriding method. I've debated about whether, I mean, we could do this. I could add another little piece of declaration that would cause it to say I actually want to be the default for this range of cases to perfectly mimic the way overriding works. But I think actually I'm not sure that's the right decision, and I just want to hold off and wait and see, get some more practice with it. The point, of course, is not to perfectly emulate the way polymorphism and overriding work in Java or whatever. The point I'm trying to make here is that the essential semantics of polymorphism is a matter of dispatching, making decisions in a partitioned nesting of your state space, and that naturally falls out of the schematic table representation once we add in the logic of nesting without subclassing, which for me gives me seems to me a nice result that these 3 very different forms of control structure can all be represented as one in one single representation. And the boundaries between them get eroded so that you can mix and match different styles very easily. You can share code across here. And I think this is a somewhat surprising result, and I think it has to be telling us something. And to me, what it's telling me is that much of the design of our programming languages is really an artifact that's constrained by the fact that text is linear, right? That these are all different control structures meant to deal with the fact that, well, the control flow is pretty much linear, and you've got to figure out ways to jump around that are easily inferable by reading the text. And if we change the underlying representation to be 2-dimensional, we get an extra degree of freedom, right? It's just natural that it's easier to lay things out when you get an extra degree of freedom. My overall conclusion is, perhaps not surprising, is that notation matters, right? To me, this has been proven over and over again in the history of science and mathematics, that the right notation is half the solution, right? The right notation should embody the semantics of its domain, mirror it in some sense, so that the changes that you can and easily make in that notation represent meaningful changes in your domain. And so that's what I've tried to get at here with the schematic table, with using canonical forms and, oh, I forgot to mention canonical forms. Oh, well, never mind. Using automatic layout generally, using unique representations for things, eliminating the noise of white space and syntactic layout and a lot of the freedom that you get in syntax to directly represent the meaning of it and to let you directly edit the meaning of your code. In a certain sense, manifesting the semantics of Boolean algebra and data flow graphs right in the user interface, rather than having to insert and delete characters in a string and imagine what the implications of that is going to be. The reason I can do this is obviously just because computers let us invent completely new kinds of notation that aren't possible on a teletype. And that's really my only real message that I'm trying to communicate, is that if we break free of the teletype, there's a whole world of possibilities open, I think, that are not really fully explored. And I hope that this means is that the history of programming languages is not over. I may be wrong, though. So I say onward into the second dimension. I have some more slides, which how are we doing on time? Looks like we're okay. And unless anybody objects, if there's any questions now, or I could just plow on to what I think might be more actually relevant to what you guys are doing. Yes?
I have a question. So how does the story change if you allow relational predicates? Right now you
Yeah.
always
With constants.
constant, right?
Yeah, yeah.
But if I want to test, say, one input is greater than the other input, then if the table is going to break down.
Well, I need some extra edges to show that. My logician friends tell me that I'm okay in terms of decidability, that adding equality to this logic doesn't break decidability. I haven't implemented it yet, though, so I know that x equals y and x not equals y are in contradiction, but I can't make inferences like x equals y and y equals z, and therefore x equals z. But that's just because I was learning about logic, decision procedures as I was doing this, and I just wanted to keep it as simple as possible for the implementation. So the theoreticians tell me that it's doable, but I'm going to need a fancier engine to do it. And I will need a little bit of extra notation to capture. So there's going to be some extra lines in there to show when two predicates are sharing the same variables.
Or also what is disjoint, right? Right now you sort of have different constants and you can sort of see directly how it is disjoint, but once you have a less than b equals nothing equals c, then it seems that disjoint is just going to be essentially functionally disjoint.
Well, I mean, the partitioning the columns, I think, still works. It may not be as clear why they're disjoint. I suppose that's a good... Oh, yeah, I can do that. I can certainly do that. But he's talking about, like if a less than b and b less than c implies that a is less than c, and therefore if you said a greater than c, that contradicts that. Well, I think it's a good question, and we have to see. I'm not sure I see exactly why it's going to be a big problem. I can see that I might need some explication for why it's drawing certain inferences. And I do have that, though. Yeah, but it's just a slight, not a more powerful engine in the logic sense. It's just that my implementation, it takes a shortcut here because I didn't have time to actually solve it. Supposedly it's logical. Adding equality to this logic doesn't change it.
Well, as you make the predicate more complicated, you're going to need a more and more powerful reasoning method.
Yes, and that's why, and let me get into that. That's why my predicates are simple on purpose. Okay, so maybe this is a good segue to talk about what I think might be some implications, and I'm not going to claim that I really have discovered anything here. You know, the point so far, the only point I've made so far, I think, is that, geez, Boolean algebra is hard to do in your heads, and it would be nice if our programming languages / tools did it for us. I'm taking the fundamental approach of trying to build it into the language. One could try to just do it at the tool level on top of an existing language. A little harder because of the semantic mismatch there. But what does this mean, though, for language design? Well, okay, so here's Alan Perlis's famous epigram, right? Programmers are not to be measured by their ingenuity and their logic, but by the completeness of their case analysis. And I'm suggesting a revision to this, which is that languages, in fact, should be measured on this basis, and that we can move this down to the language / tool level rather than relying on programmers to be smart enough to do it. The power, I think, what I learned doing this is that, what was surprising to me, is the power that I got from static analysis of declarative conditionals. What I did was I restricted the expressiveness of conditionals. Exactly one case must be true. There's no else shortcut. You could imagine taking Dijkstra's guarded command language, right, and forcing one case to always be true and eliminating all indeterminacy in it. That would seem like a real loss in expressiveness. I'm also restricting the expressiveness of the conditions themselves. I'm using a very small decidable logic. I can only say certain things. And I'm using exactly the same logic for runtime assertions. And that turns out to be very useful. The fact that conditions and assertions are the same thing, use the same logic. You can make all these inferences about them. So, you know, my good example is you test if something is type of foo, and then you cast it to foo. I mean, what's that cast doing there, right? It's because the type system isn't smart enough to know it's inside that conditional. Right? So here we know that already inside the conditional. There's a lot of things like that. but it's still really restricting the expressiveness. I only know certain things. But it seems that most of the times, things we do switch statements on, polymorphic dispatch, are on very simple decidable logics. And that's what I'm pointing out here, is, you know, finding your way up and down a nested partitioning is not a hard problem. So I restrict the expressiveness I'm allowing inside conditions, and I gain a lot of static knowledge of the behavior. And this knowledge is decoupled from the semantics. It's not wired in like a traditional type system. So one can start adding inferencing engines if one so feels like it. You could add theorem provers, whatever. Any smarts you want to add here that can tell the programmer more is okay, because it doesn't change the meaning of the program. It just changes what the user interface is telling you about the program as you're editing it. And there's another surprising thing about these little places where we saw kind of type-like behavior popping up, even though this is a dynamically typed language. And I mean, if I can sort of stretch a metaphor here, I think of it as that types reason vertically through computations, right? And that's a hard thing to do. It's hard to do decidably. And one of the rules of it is subsumption, right? That supertypes are okay, subtypes are okay. That's weird. Yeah, subtypes are okay. Sorry. Whereas logical analysis is horizontal. It's within a given state, not across states. And it's all about partitioning up the state. And that's an easier thing to do. And it's governed by this intersection rule that allows supertypes or subtypes to be acceptable. That's a lot weaker. But it eliminates all this contravariant stuff that's a thorn in lots of theories. And what's paradoxical, I think, is that because it's weaker, it becomes more expressive within the bounds of decidability. So I can throw in assertions about, like, integers being positive. And doing a type system with that is hard. I've never seen one in practice. But it's okay, because I'm trying to only come up with weaker conclusions. But those weaker conclusions are useful to the programmer. And so my hypothesis is that I'm going to lose some things, like places where people pass a supertype where a subtype is expected. I'm not going to catch that error anymore. But I'm going to catch a bunch of other errors that a decidable type system can't capture, and that this may be a good trade-off. Finally, and to even become even more wild-eyed hand-waving here, in the future I'm thinking that, so my assertions currently were at the top level. You could put them on inputs and outputs, but that's it. What about putting assertions inside conditionals, inside the code? Then you're actually, like someone mentioned before, you're making pre-post condition assertions about the code. And even better, if once I add some iteration here, assertions inside iteration gives you quantification, first order logic. So do we get to the point where the logical analysis of this language can actually express a specification for a program? And this has been done before. The only interesting thing about it is that doing it in a single language, where the specification is sort of its static semantics and the implementation is its dynamic semantics. But there's one language and one set of semantics, rather than sort of gluing a specification language onto a programming language. I'd be happy for anybody to shoot down this idea, because you guys know more about this stuff than I do. But it seems to me a tantalizing thing and to work on. Thanks.
So, going back to the polymorphism example, I suppose this is ultimately a scalability question, as no doubt there's a multitude of things that fall into that category. So your example is basically decomposing one function, a hack function, and using polymorphism to do some of the case analysis in it, right? And it's really nice the way the pieces all pop up there in your charts. But so that sort of composition in slightly larger programs, you start
sharing between the decomposed pieces, between multiple
Multiple inheritance.
Well, it's multiple top-level computations. You know, in addition to just having an attack function decompose, you might have a health function or something that also made use of power or something that was factored out, and so
Okay.
these
So that would be a reason for more fine-grained methods, you mean?
right, and so these methods that were essentially represented, these overridden methods that represented the various conditional clauses would tend to be shared across multiple of these top-level propositions, and so you wouldn't. You could look at any one of them and get a picture like you have there, but when you try to sort of understand kind of the overall structure of the decomposition, sorts of things that people who do object-oriented design tend to think about, it's not clear how you would see that.
Well, I mean, that's really not, I mean, that's just functional abstraction, right? That's just, you know, you have some shared code in two places, pull it out.
Right. So you would have to represent that.
So it moves to it.
Functions.
Yeah, right. It becomes a separate table at that point. Yeah, absolutely. You have to do that. What's nice here, though, is that my model of function calling is essentially edit time inlining. So you could see you could always right-click there on one of those little triangle thingies and see the code you're pulling in. So instead of it just being a, you know, long string of camel case words, you could actually see what it's doing, which cuts down the abstraction penalty for understanding what's going on. But I don't have any magic for, well, actually I do. I just haven't tried using it yet, actually. So I am thinking about ways of sharing code not through strictly functions, actually sort of more intrusive sharing that breaks through the boundaries of functions. But I haven't really done that yet. I guess I'm not really ready to claim that it's a solution.
And I say a lot of this is fundamentally about scalability, and it's like, I mean, you kind of went from the 5 statement to the 30 statement. Now, what happens when you go to 200 statements?
Absolutely. So I'm crawling here. Okay, this is taking baby steps, just trying to isolate some issues that there might be room for improvement. But obviously, scaling this to large-scale software development, you know, is a whole host of questions. But the thing is, we've gone pretty far from punched cards, haven't we? I mean, we've learned how to scale that pretty well, and we've used a lot of cleverness. So my reason for optimism is simply that, you know, when we encode programs as text, we've essentially locked ourselves into a user interface. Whereas what I have is a model view separation here. I've got an underlying model, which I could show you about what's going on, but it's meant to be a simple, semi-simple, abstract model of the semantics of the program. And then I build this UI. So the whole thing here, columns, rows, none of that exists in the actual representation of the program. It's all inferred from static analysis of the code. Code is actually this complex tree-like thing with links all over the place. So this means that you're free to change the user interface without changing the code. And if you invent a better UI, you can just plug it in and use it. Whereas with text, we're stuck, right? Because we've added those spaces and carriage returns, and you damn well better not, you know, change those on me because it's important to my understanding of the code. So I've broken that coupling, and so I think that it leaves room for innovation, which is a weak answer, but. Onion?
So what happens to the sort of editing or development experience when the logic implementation is not complete? Because I don't know how smart your engine is, but if it can't figure something out, you're going to get these gaps or other issues, and then you're basically stuck, right? You can't really complete the program. Is that right? Or is there some way out of this?
Yeah, you put in assertions. So if you know something that it doesn't know that's important, then you just add the assertion, and it's okay at that point. And I think that's a good thing, because what it means is that if the simple static analysis of this code can't tell you that you're doing something, that you're not doing something stupid, then you should be explaining why that's the case, because someone else reading your code probably doesn't understand it either. And so actually forcing you to put in those assertions, as long as it's not onerous, but putting in some assertions to say, well, in fact, these two things can't be true at the same time. But to know that, you'd have to know something about, like, algebraic properties of addition, right? Well, you know, instead of adding a theorem prover that knows about that, I just say put in the assertions that claim that to guarantee that the logical analysis is correct.
Okay. Yeah, that makes a lot of sense. So where in the table would you put this into?
Well, you can put assertions inside the columns, you know, that are only true or only expected to be true for that condition. I didn't show that at all. I had all my assertions were over in the left-hand column. And in fact, I'm not even sure I'm supporting that yet in this implementation, but you could put assertions anywhere in the code in those columns, and it's part of the column, and it says that if all the conditions in that column are true, then all the assertions in the column must be true at runtime, right? And so all this static analysis I'm doing here is backed up by the fact that it's also checking at runtime all of this stuff, and a smart compiler would use the static analysis to get rid of the runtime checks, right? Okay, well, that's everything. Again, I'm not sure how this is going to affect shipping code anytime soon, but just want to throw out some strange ideas and maybe influence thinking in the future. And I'm happy to talk more about this stuff with anybody. Thank you.